All right, ladies and gentlemen, I'm just going to get through this as quick as I can. I have an idea. Now, I've built a lot of wings. If you go back and look at my Batwing channel, just kidding. I've made a Batwing on that channel. It's actually up, has been for, I guess about 2 years now. I have a ton of small aircraft that I have designed. I've been working on aircraft design since I was a little kid. Now, traditionally, the control surfaces are at the rear of the aircraft. Now, I'm just using this because, well, this one's a fine example. It has a good combination of control surfaces on it, and I can kind of use it to show you some stuff. Now, you'll notice that the nose on this is angled upward. This is actually a lifting surface, causing the air to speed down here, slow down coming up, then speed up, helping to overcome the drag induced by that slowing down, and then having it slow down again as it comes up the canopy, only to be trapped here in the engine compartment for its ducted fan. That was the plan. It's a good design and it flies very well. It works very well. There are a lot of things in engineering you could do like that really change the way an aircraft flies. This tends to make it land like this no matter what. It kind of looks like the space shuttle coming in for landing, but it makes it so that it lands very equally and doesn't tend to want to tip stall. That was the purpose of the design. Well, earlier today, I had a bit of an epiphany. Now, traditionally, we operate an aircraft by control surfaces that operate along the back of the wings, but that creates a few problems. Now, when I was designing the Batwing, if you go back, you'll see that when I show you the Batwing, I show you that all it takes is a little tip sticking out and you bending that down a tiny little bit to give you the same amount of lift that the entire wing normally gives you by having a camber. I've done that with a flat wing on that aircraft. Now, it does have a little twist, but it is a flat wing with no camber, no arch whatsoever to it, folks. Absolutely none like this. It is a flat wing. This one has no twist. It has a tiny little bit of dihedral, but that's about it. It has a lot of rake and some dihedral, but we're getting technical. Sorry about that. But in the end, it doesn't have the traditional, it's a wide wing that's thick. And the reason is this here. This is a lift device. This is a VG that runs the entire length of the front of the wing. And this turned out to generate as much lift as an entire wing does. Only it's only the leading edge that's making the lift. And with this extra structure, it makes that leading edge so stiff and strong, all the back has to do is let the wind slough off it as quickly as possible. And you have a very high lift setup that is also very low drag, allowing you to make a thinner wing that is overall lower drag and still very high lift. I've done a lot of really brilliant stuff in aeronautical engineering. My contributions are kind of getting legendary, to be honest with you. But I'm not done yet. And this one's the biggest one yet. Because normally, you control an aircraft at the back. Let's think about what that means for a minute. For one, it means you have to run linkages up the length of the aircraft. The higher the performance, the farther out at the tip that weight is, because the farther out towards the tip the ailerons generally are, which means you're running a rod the length of the wing that runs from inside the body, unless you're running fly-by-wire. And even if you're not, you've now added a lot of structure around the aileron in weight. At the back of the wing is bad. Any added weight there is bad. It's better to keep all the weight forward on the control surfaces. I've also learned, for purposes of speed, it's better to keep the lift at the front of the wing. It helps it to climb rather than just try and do this. When it tries to do this, there's a lot of air resistance above it, like a parachute catching it. Try putting your hand underwater. Do this and push it through the water versus doing this. Well, it's the same thing. When it's trying to come up, we want it to come up on a 45-degree angle. That is the best angle for climb speed, believe it or not. Just like in the water, if you wanted to sink or raise a boat, I'm a salver, I know, 45 degrees is the angle. In water, it's just nature. And in air, it's the same thing. It's the reason the space shuttle comes down at this angle. It may not be climbing, but it's still coming down with the body at a 45 angle, while relative to that, it comes down at a 45 angle, and the two intersect at a perfect 90 when you look at the aircraft and the line of travel of the aircraft, they actually do intersect perfect at a 90-degree angle with the plane of the aircraft. And it's like, hmm, it's just one of those things. You see it settled onto this angle, it's traveling down, but it's really not. It's really traveling perpendicular. Well, that's what you want. If it's at a 90-degree angle, you get bad things happening. What you want is for the direction of travel that it wants to travel, that it's naturally aerodynamically inclined to travel, to be its glide path without aileron input. That was part of the goal of the aeronautical engineering project I'd last did. But during the course of that, I wanted to show that you could make a variety of lifting wings a variety of ways, and that a flat wing was absolutely possible. And this is one very fine example of that. Now, normally we control something at the back of the control surfaces, but not only does this add weight to the back of the wing, making it more prone to stalls, but also making the wing more complex. At the back of the wing is the best place to have it be thin. But by adding control surfaces there, you create a lot of issues. Now, when I did the Batwing project, anybody who's built a Batwing can tell you that those points have to be exactly straight or just bent down the tiniest little bit. If your wing is flat and they are bent down the tiniest little bit, those 2 points on the tips of those wings, that's it. That's enough, that it creates enough lift to fly that much bigger and heavier than this aircraft with much less technical lifting surface. See, I've realized it's not the size of the wing. It's not the size of the surface area that is doing the lifting. It's how much lift you get and where that lift is generated. By generating the lift here, you are generating the lift at the CG of the airplane, making it want to do this. By generating the lift at the front of the wing, it wants to do this. It naturally pushes the wing up and it starts to climb closer to that 45-degree angle. That is actually a good thing and helps the aircraft climb better. Now, that's one thing. There's lots of brilliant bits in this design, believe it or not, as simple as it is. But the most brilliant one I just came up with today. So instead of having my control surfaces at the back of the wing, I'm going to have them at the front of the wing, where it's generating the lift. By the same token, I need very small amount of this to generate the lift. And by putting them here, I can use them to fine-tune my lift and use them as a combination of flaps, ailerons at the same time, meaning they're automatically flaperons essentially, because I can control them to make the wing a superstall wing if I want. Well, that is actually the most effective way to control the airplane, it turns out, not from the tail. That's the most ineffective way, as anybody who's ever flown a 2 or 3 channel airplane can tell you. You don't start to get real control until you can use the ailerons and the elevator. Now, the elevator isn't necessarily best off controlled at the front, you might think, but the same physics apply, where that one little tip angled down does so much more than that whole lifting surface with that big flap at the back of it sticking out. Because that flap sticking up is creating a ton of drag, and the pivot point is now the back of the airplane. You're trying to make this whole thing pivot from here. Well, now you have a long moment here, a long pendulum, and it takes a lot of force to move that pendulum. The faster you're going, the more force it takes. But the further up you move that control point, the shorter the pendulum gets and the less control force it takes. At the same time, at the leading edge is where they're most sensitive to control inputs. It's where the smallest input makes the biggest difference to actual aircraft flight. Which means, unlike putting it at the rear, where you put all the weight at the back of the control surface, you put the weight at the back of the wing, you put that extra structure, that's extra weight that you have to make the back of the wing a certain thickness to accommodate all that structure. It's been said for a long time, you can make the wing a lot thinner without that structure. This is how my airplane's going to be. That structure won't be there. Instead, it'll be here, where it has to be anyway, at the front of the leading edge, and it's just going to have like a little boot that is attached to the tip. So the tip will be smoothed and rounded with a hinged boot that is a pyramid that does this. That's it. And that is going to give you yaw control. On the leading edges, it's the same thing, and it moves back and forth. And I don't know if you knew this, but for de-icing, all you have to do is wiggle those, which gives it built-in mechanical de-icing that no one's ever had before. And every time you operate your control surfaces, you're de-icing them, which means it's pretty cool. It had so many advantages. And it only occurred to me recently that this was even possible. Nobody's ever done this before. But I have done enough experimentation already to know that it is the best way to control the airplane. And by that, I mean you will need the least amount of control input because it's incredibly sensitive. When I was making my Batwing, I had to do a lot of screwing around to get them to even fly correctly because it was making so much lift, it was flipping the front of it over backwards, even when I put a fair bit of weight in it. Now, that's the other thing. As a superstall kit, think about you want low drag and high lift, not high drag to create lift. I do not think in terms of vortex generators. I do not make vortex generators. None of these are vortex generators. They're lift generators. But when these move up and down, when those leading edge slats move up and down, they are creating that vortex as it comes up over the leading edge. And that gives you a thick leading edge that you can then adjust and make thinner or thicker, essentially. Angle that leading edge of it is all you have to do. And it changes its relationship to the air. It also acts as your trim, allowing you to trim in the airplane, which means you don't need a separate trim tab anymore, which again takes away weight from the back of the aircraft, which means the back of aircraft wings could be this clean, guys. No bullshit. I know it sounds unbelievable, but it's all true. And these principles are known already. They work. And just like this, flew incredibly well with this little tiny bit of an upturned nose. Now, I did this because if you look, you'll see that there was something inserted here, and it's because I was slingshotting this with a catapult, and I had a paperclip installed here with some glue, and that is actually my nose weight, and without it, it won't fly right. It's just, but it makes lots of lift, and it's nicely balanced right now. Even as it sits, it actually CGs very well and all that. And this is one of the things that you see with an airplane that's CG'd right. Now look at that. It CG's right at the front of the wing, but not quite. It CG's so far forward, guys, it's like right here. Okay, this is one of my balancing marks. I actually made two little marks here when I first built it, and you can see them here. Two little marks to make my balancer, and that's where it balanced perfect. And so that's without the nose weight. Now, with this, it's perfect for a light glide, but if I wanted to survive a catapult launch, it needs more nose weight. Now, that brings up a whole nother batch of physics, but I found the same thing with a catapult launch. This leading edge strengthening of the wing does a lot more to make the wing resistant to ripping off or folding than just making the wing thicker in the midsection because, well, this helps prevent any flap along the leading edge. That twist it encounters at the leading edge has a lot to do with how the rest of the wing responds, and this makes like an L-beam where it's a very strong structural shape up against the side of the body here. All that matters, and all those are good features of this little airplane. But you also notice I've done the VG kit in two different sections here, front and back, and it's separated here for a reason. It's a bit less smooth, but you can see the shape here, and it cuts in a little bit. That's actually intentional and makes it so that it makes like a little trap here for air and helps it to create airflow there. But it's also because these are actually going to be my ailerons right here, just that little forward lip. And it's just going to be, this is without the lip added. So I'm going to add an additional lip on here, which will give the wing a dog tooth, like a fighter plane, which is also known to be a very effective situation. And then this portion of the wing could actually build ice, but it would only increase the lift. Normally, adding ice to the leading edge of the wing corrupts your lift, but when that's where your lift is made, adding thickness here is actually okay. And if you don't have your control surfaces vulnerable to icing in the rear, making it weighted and making it want to go down, this encourages the weight that it does pick up in ice to be along that leading edge. And if your slats run the entire way, and we've got a boot here and a boot here, they can move in opposite directions. The inboard ones would actually be the ailerons, outboard ones could be for trim, or vice versa. You could just have them for boots. Maybe just make these ones expandable, but I like the mechanical method where they just move up and down. And that would mean I will use the inboard set for trim and the outboard set for control. And that'll be the same thing as it having flaps. And it works, guys. Also, by moving one set of tips up and the other set of tips down, it'll achieve basically a flap operation, which is really nice. It's basically like flaperons. Um, and at the same time, here, it's the same thing, except this is the one place where it's actually better to pivot from the rear. If I pivot from here, no, it's the same thing, you might think. And you're right. Because at the back, you have a longer moment, you have a longer pivot point. It's farther back. But up here, it takes very little effort to move this. And so right here, if this section is able to just lean a little bit right and left, it would probably only have to move a few degrees, guys. And that's the other thing. If I do this with normal flaps and ailerons, I need a lot of deflection, we call it. And that is the angle that the ailerons are going to move to up and down. That's their deflection angles. So they have a positive and a negative deflection up and down. Well, without getting into all that, this has no deflection angles at the rear, which is where it's most sensitive to really corrupting the lift. No, but it is more sensitive there to wrecking the airflow. You want the airflow coming off the back to be as smooth as possible, not corrupted. That helps it to fly better and faster and with less interference, less created drag by actuating the control surfaces. You will slow down less, and this system automatically generates lift, which means as you pull up, when you go to land, it's automatically creating something of a flap at the leading edge and creating like a stall section just by you pulling up, which is pretty cool. And when you nose down, it takes that away, removing that extra lift and making it very sensitive, because not only are you lowering it, but you're reducing the lift of the wing at the exact same time. So it gets very sensitive. When you go to raise it, every millimeter you're raising it is increasing the lift of the wing, which means with only about 3.5 to 6.5 millimeters of travel on that tip, you'll get enough actuation that you won't need anything else. That's my guess. It'll be such a small amount of travel, no more than an inch. I know that because when I set these up and fly them as RCs, I have to use minimum control inputs, like really sensitive on the controls they get until I really dial them back digitally. Because the bat wings with that setup are so sensitive, guys. And what I've discovered by controlling things this method and by CG is that they are incredibly sensitive this way, which means you need a very small control surface to move to actually affect this. And so this is my design. It's going to be incredible. This is going to be my ultralight jet. It's going to be EDF powered, and it will make good speed with less thrust because it will be light. And as you can see by the design, it is an incredibly light design, guys. Sorry to bug you for 20 minutes, but I also will point out that this involves something of what you might call the area rule, where the canopy is in a very specific spot, and I have modified the area rule for those of you who are familiar with it. If you take a good look at my design, this turned out to be really good for a lot of things, and I thought that those of you who are aeronautical engineers would really like to see this. I know that Canada and the US are both working on new fighter planes right now. Unfortunately, I don't even have CAD, guys. I can't even come up with a viable design for you. The best I can do is tell you that this was intended to be a fighter trainer of a new generation for a new age. Keep that